So welcome to today's class, and today we are looking at regression with qualitative information. In our previous classes, or even in our previous units or courses, we have looked at regression with quantitative data. So more specifically, we have been looking at a case where the dependent variable is a continuous variable. So in this class, we want to introduce a regression with data which is not qualitative. And when you talk about, data which is not quantitative, when you talk about qualitative data, you may want to recall this, that qualitative, let's call it qualitative variable, is a variable. Yeah, so this is a variable whose data takes non-numeric values. Usually we say takes the form of, so this data usually takes the form of names or labels. Usually takes names or labels. Okay, so this is also called let's say this type of variables are also called categorical variables. They're also called categorical variables. So sometimes these names are used interchangeably: qualitative variables and categorical variables. The opposite is what you call quantitative. And remember, as we said in our previous classes, quantitative variables, they are variables whose data takes numeric forms. The data is in form of numbers. And from the quantitative variables, we have continuous variables and discrete variables. Okay. Then today we are looking at qualitative variables and how we can use them in regression analysis. For example, an example of what you're calling qualitative variables is, for instance, this might be your research question. A family owns a car or not. So you may be interested in finding out whether a given or a particular family, let's say a random family, owns a car or does not own a car. Or we can say that any given family either owns a car or does not own a car. Okay. Then you can also have a person either smokes or does not smoke. So this is now what we should be calling the qualitative information. A person either smokes or does not smoke. Then we can say that a person is either male, a person is either, let's say, of male or female gender. A person is either of male or female gender. When you sit for an exam, you either pass or you fail. So that is what you're calling qualitative information. And that's what is coming from qualitative variables. Okay. Then we notice that in regression analysis, some of these variables either come as a dependent variable. So they are either dependent variables or independent variables. And you notice that technically, these kind of variables are coded by binary. They are coded by binary values. Binary means two, signifies two. Bi signifies two. So binary values, that is 1 if the answer is yes, and then you say 0 if the answer is no. So for instance, if your interest is whether a family owns a car or not, then the answer is either yes or no. If you ask this question, do you own a car or do you own a family car? The answer will either be yes or no. So we say instead of writing the words yes or no, we code it. We code the responses into 0 and 1. So we try to write the answers in form of numbers. Remember, we said that the categorical variables, they give data which is in form of names or labels. So instead of working with the names, yes or no, we code it. We code the data into ones and zeros, where 1 signifies a yes answer and 0 signifies a no answer. Okay. Then we say that in econometrics, these variables are called dummy variables. They are called dummy variables. So we create what we call dummy variables. We note that the usual practice is that, or we can say that the usual practice is to denote. The usual practice is to denote the dummy variable by the name of one of the categories. By the name of one of the categories. So instead of having this as your variable name, instead of having this as your variable name, you choose one of the categories, one of the possible answers as the name of the variable. But that new variable is called a dummy variable. So for instance, if you want to find out or to collect information on whether a random person smokes or not, instead of writing this as your variable, you just have the column name or the variable name as smokes. And then below there, so you'll have something like this. So you'll be having, let's say you have several other variables, but now you have this one, you call it smokes. So meaning that, so here we have the individuals. Here we have the individuals 1, 2, all the way to n. So you'll be saying either yes or no, yes or no, yes or no. So what we have here is what we call a dummy variable. This is what we're calling a dummy variable. And we are saying that instead of you writing the word yes, you usually write 1, and here you write 0, 1, 0, 1, 0, maybe 1, maybe there are several smokers there, and so on and so forth, 0, 0, 1, and so on and so forth. So your data will look like that. Your data will look like that. The same case in case of, let's say you are interested in finding out whether the person you are interviewing is married or not. If you want to find out whether the person you are interviewing is married or not, because you are either married or you are not married. Okay, you can be in both. So instead of having the question name as "Are you married?" That being the title of your variable, you can choose one of the categories as your dummy variable. So you can say married. You can capture that. Then you'll be writing 0, 0, 0, maybe 1, 2, 0, 1, etc. So saying either yes or no, saying yes or no for all the individuals. So that's what we call, or those are what we call dummy variables. Those are what we call dummy. So for instance, we can say, instead of using gender, instead of having a variable called gender, we can define the variable one can define the variable as, say, female. You can just call the variable female. Instead of using this as your variable name, you just call the variable female, which equals to 1, or which takes the value 1, which takes the value 1 if the individual is of the female gender. It takes the values 1 if the person or if the individual is of the female gender, and 0 if the individual is of the male gender, Okay. So it takes the binary values 0 or 1. So if the person being interviewed is female, you write 1. If it's a male person, you write 0, and so on and so forth. Then you say that in this case, the male gender, that is the one that is attracting the value 0, is called the reference category. Is called the reference category. So in short, we set one of the categories as a reference category. Okay. So basically, that's what you call, or those are what you call qualitative or categorical variables. It's good for you to note the concept of dummy variables, because we shall be using dummy variables in the next session. Okay. So I want us to look at a case where we have single binary independent variables. So case 1. So we're going to have case 1 where we're talking about the independent variables, and also case 2 when we're talking about the dependent variables being categorical. So case 1, when we have single binary variables. So maybe before I proceed, I need to mention that the number of categories are not necessarily 2. They can be more than 2. So you can have 3 categories, you can have 4 categories, or even more categories. So if that is the case, you need to be careful about how you create your dummy variables. For instance, if you're talking about the party affiliation, and you have the Democrats, you have the Republicans, and then you have others. So in such a case, you're going to have 2 dummy variables. In short, the number of dummy variables will always be the number of categories minus 1. Like in this case of gender, there are 2 categories, female or male. So the number of dummy variables was 1, that is 2 minus 1. If you have a variable which has 3 categories, then the number of dummy variables will be like in this case, will be 3 minus 1, which is 2. So you will have 2 dummy variables where one of them is the Democrat, so which takes the value 0 or 1, where it is 1 if the person that you are interviewing is a Democrat, is a Democratic Party member, and 0 if it is a Republican or other. Then you also have another dummy variable called Republican, which will be taking the values 0 or 1. So if somebody is a member of the Republican Party, you'll be putting 1. But if he's a member of Democratic Party or the other parties, you put 0. So in this case, we'll have 2 dummy variables. So you cannot have a dummy variable for the other parties. No, you only have 2 dummy variables. Then in this case, it means that this is your reference category. That's your reference category in all the cases. Huh? Okay, so let's look at cases where we have single binary independent variables. I'm talking about independent variables here. I need to put here independent variables. Independent variables. So we start by noting that dummy variables can be incorporated. Dummy variables can be incorporated into a regression model as either dependent or independent variables Okay, so but here we are starting with so here in this section we focus on the case where the variable is used as an independent variable, where in cases where the variable is used as an independent variable. Okay, so let's consider the simple regression model including one dummy variable. This is how you'll have the model looking like. So you'll have y is equal, assume y is the dependent variable, y is beta naught. So in this case, y is a continuous variable, beta naught plus delta naught. Then I have b for dummy plus beta 1 x plus the error term. So let's consider that model where d takes, where this is how you usually write it. Or let me just write in words. So where d takes the value 1 when the individual has the property of interest, or has the property, let's say, of interest, and 0 otherwise. That is, if the person does not contain the property of interest. So we are saying that d, this is how usually you denote it. Takes the value 1 if yes, and 0 otherwise. Okay, so for instance, if d is the dummy for gender female, so you can have a female. Let's do this. If d is the dummy for gender, you can have something like this. You have gender, you have 1 if female, 0 if otherwise. So this is when you have set the dummy variable and you have given it the name female. If this, for instance, if this was reading female, then this d will be the dummy for the variable called gender, and it will be taking the value 1 every time you have a female individual and 0 otherwise. Okay, so that's what you call a dummy variable. Yeah, so you can consider that example. So gender is equal to 1 if female and 0 otherwise. So in this case, it means that the model will look like this. We'll have something like this: beta naught plus delta 1 female. We'll be having something like that, plus beta 1 of x plus a u. Okay, so this is the dummy for gender. This is the dummy variable for gender. That's how you interpret it. It will be taking here will be putting 1 if you're talking about a female person, and 0 if you're talking about the other gender. Then we note that the parameter delta naught indicates the the difference, gets the difference with respect to the reference group, or the reference category. That is when D is equal to 1. Sorry, when D is equal to 0. When D is equal to 0. For the and we're saying for the reference group for which the parameter is beta naught. I'm going to give a practical illustration to see what we mean by this point. So let's consider the following illustration. Consider the following illustration where gender is modeled with male as the reference category. With male as the reference category. The model, in this model, we have wage is equal to beta naught plus delta naught, then we have D plus beta 1 of education. You can put this if you want, you can put that. Okay, so even this will be an estimator, but we can just have it like that for the sake of illustration. So let's consider this model where we are predicting the wage of an individual based on the gender and the education level. And then we are using gender, we are modeling gender as we know that gender is a categorical variable. So we're using male as the reference category as shown here. So it means that we shall be using an expression of this kind. So gender will be looking like this. We'll be taking the value 1 if you're talking about a female individual, or 0 otherwise, So I want us to present this information graphically. I want us to present, to sketch this, the kind of model here. So we can have something like this, where on the vertical axis we have wage. Then here we have education on this axis. Then we have straight line. Then we have another one down here. The two lines are parallel. So the blue line represents the predicted wage of males. The predicted wage of males or men. So this is for the males. Let's call them men. Men, wage is given by, or the estimated wage is given by beta naught plus beta 1 education. I hope you can see that, because you are saying that for the males, you put 0 here. So once you put 0 here, this item goes away. You are left with this model. So that's how you predict the wage for males. Then for the females, it is the model the way it is. But now here, where there is D, you put 1. Where there is D, you put 1. So you'll end up with, sorry, I need to say, for the females, the estimated wage is given by beta naught plus delta naught plus beta 1 education. So for the females, that's how you predict their wage. So you notice that this is what I was saying in this statement, that the difference, this value here, the parameter delta naught is the difference between the two categories of the dummy variable. So this is the model for the males, and this is a model for the females. The difference between these two models is just this guy here, because you notice we have that, it is here, also there. So the difference is only this. So this is the difference between the way holding the other factors constant. This will be the difference between the estimated age of males and females. Okay. So basically that should be it. So we can say that if you set this one to be your beta naught plus delta, this will be your beta naught plus delta naught. That's for the females. And then this length here will be beta naught like that. Beta naught like that. Delta naught can be plus or minus. So in this case, it looks like it's a negative value. So you find that this value here is smaller than this value alone there. Okay, but the slope is the same. This is the slope of each of the lines. The slope is the same. So that's why the two lines are parallel lines. Then we can say that the category, we can say that the category with B is equal to 0, that is for the males, we say that makes the reference category, and D naught or delta naught indicates the shift, or change in the intercept, with respect to the reference category, with respect to let's say with respect to the reference category, with respect to the reference category, sorry. Okay. Then now, how do we interpret? So we're saying that this gap here is what we are calling, and that's the difference between the males. These are the males and the females. The difference is delta naught if you hold the other factors constant. Okay, so let's look at the interpretation of models with dummy variables. Interpretation of models with dummy variables. And I want us to consider example. So example, let's say, suppose we are interested about the difference, or we are interested in the difference between the wage levels of men and women using the following model. So suppose our interest is to find the difference in wage levels for both, for male and female individuals. And then we're using this model that wage is equal to beta naught plus delta naught, and here we have female. So that tells you that is our dummy variable, plus beta 1 education plus beta 2 experience, and then we have plus beta 3 tenure plus the error term. So that's the model you want to use, and then you are given the following output. So this is the output when you analyze the data using your software of choice. So you'll have the coefficients are here, the intercept, the coefficient for the female gender, the coefficient for education, experience, and tenure. Then we have the standard errors and the t-values. Then the model for female will be given by this. The estimated wage for females will be given by this to be the estimate, the intercept plus D naught or delta naught and the other coefficients. Okay, so if you substitute, we'll get this minus 1.57 plus minus 1.81. So this is your beta naught estimate, and this is your delta naught. This is your delta naught. Then this is your beta 1, beta 2 is here, 0.3 over experience plus 0.14 of the tenure. So you have such a model. So when you simplify this, you can leave it like that. I can leave it like that for the sake of illustration, wage for females. But you can combine this and get the value here is minus 1.57 minus 1.81. So this is the same as minus 3.38 plus 0.57 education plus 0.03 experience plus 0.14 of the tenure. So that's the model of estimating or predicting wage for the females. And for the males, we do the same thing. For males, the wage estimated for the males will be equal to, now where we have D naught, we'll be having, so here we put 0. In this model here we put 0. So once you put 0 here, even this coefficient goes away. So we're left with the intercept, then the remaining ones. So this will be equal to minus 1.57 plus 0.57 education plus 0.03 experience plus 0.14 of the tenure. So that's how you predict the wage for the males. That's how you predict the wage for the males. Okay, so the question is the difference. So in general, let me write this generally. This is the same as wage for males is the same as beta naught. All these are estimates plus beta 1 education plus beta 2 of experience plus beta 3 of the tenure. Okay, so that's the general model compared to these. So if you want to find the difference between the male and the female, so we say that because this is multiple regression, so you need to hold the other factors or the other variables constant. So you can say that holding the other variables constant, the difference in wage levels, between male and females is given by you can just take the first equation minus the second equation. You just take this minus that. This is the same as the estimated wage of females minus the estimated wage of the males. And this will be equal to delta naught. It should be easy for you to see that. If you take this minus that, you'll find that the difference will only be this item here. The same case, if you take this equation minus this equation, you'll notice that the difference between those two is just this value here. The difference is just that value there, which is our delta naught. Okay. So that is it. You can have this as an exercise. And the question is, how would you interpret? How would you interpret the change in the model is log of wage? You change, if you transform the wage using log is equal to beta naught plus delta naught of female plus beta 1 education plus beta 2 experience plus beta 3 over beta 3 of tenure plus u. If that is your new model where you transform the dependent variable, how would you interpret the difference between the level of wage for males and females? It's good for you to note that because we have transformed the left-hand side using logs, then if you take 100 delta of naught indicates, so this is the hint. If you take 100, if you multiply delta naught by 100, so this will indicate the difference, percentage. So it will tell you the percentage difference of the levels of wage for those two groups. So basically that's what we do. This is a log level model. Okay. So you can perform this analysis using Excel. I guess this data is available in the Moodle or the DL platform. You can check out this data and run the regression in Excel using log of wage. Okay, so I want us to look at cases where we have multiple independent dummy variables. When you have more than one dummy variable as independent variables. So multiple independent dummy variables. We can start by saying that additional dummy variables can be included to the regression model, as well. Okay, then we can say in the wages example, in the above example, on wages, if married, if we can have another variable here called a dummy variable called married, which takes the value 1 if the person is married, and 0 otherwise. So in the above example, if married is included, we have the following possibilities. So you can, let's summarize the number of, there are 4 possible interpretations. So we have the first dummy variable called the female. Then we have another dummy variable called married. Then the possible interpretation So if we have a 1 here, that means if the person is female, it is possible we can have a female, then the person is married. Sorry, is not married. A female who is a person who is female and is not married. So this is the same as a single woman, not married, single woman. Then you can have a person who is female, but they are married. So this is a married woman. Married woman. Then you can have a person who is not female. They can also be married. So they can be married, yes. So this is a married man. Married man. And finally, you can have a 0 here and a 0 there, which means we have a single man. So those are the possible interpretations if you have two dummy variables in that model. So let's have some illustration. Consider the model. Consider the model. We have log of wage is equal to beta naught plus delta naught female plus delta 1 married plus beta 2 education plus we can have beta 3. This is experience. Then we have beta 4, which is the tenure plus the error term. So this is similar to the first model, or to the model that we fitted in the above section, but now we are adding this new variable here, which is a dummy variable, taking the values 1 if the person is married, or 0 if the person is not married. So this data is, I can illustrate how the data looks like because I have it somewhere here. So this data looks like this. So this is the data that we are working with, the wages data. As you can see, we have the wage, education, all these are continuous variables, the tenure, then we have non-white. This is an example of a dummy variable. So a person, a given individual is either non-white or they are white. So in this column, you expect a 1 if the person is non-white and 0 if the person is white. Then the dummy variable for gender is here. So we are calling it female, which takes the values 1 if the person or if the individual is female and 0 otherwise. And we have the one for married, which takes 1 if the person is actually married and 0 if the person is not married, and so on and so forth. So this is basically how you capture your data in dummy, using dummy variables. It only takes the values 0 or 1. So in these 3 columns, the ones we are considering, we have either 0 or 1. So 0, 1 everywhere. Okay. So let's move on. Okay, so let's consider the output below, which comes from that model. So we have this. I've left out the columns for T and P value. Those ones can be easily computed, but now we don't need them. Then the required, we have 2 parts. Interpret all the regression coefficients in the fitted model. So you interpret each of these values. Okay, it's good for you to note that in the interpretation that we are fitting a log level model. So your interpretation will be in terms of percentage, the percentage change in the wage for a unit increase in the other variables, for a unit increase in the continuous variables. Then for the female and the married, you'll be interpreting the way we interpreted example number 1. Then the required second part is that you find the estimated wage of a single woman whose education is 8, experience is 44, and tenure is, did I say 88? No, this is 28. Huh? This is 28. Okay. So we just need to substitute these values into the model. And you notice that single means that married is equal to 0. Married is equal to 0, and female is equal to 1. So those are the values that we'll be putting here. You put 1 there, you multiply this by 1, you multiply this by 0. So you'll be left with this item. This will go away, and that, and that, and that. And you simplify to get the percentage change in the wage. Okay. All right. So so that should be it regarding the use of independent dummy variables. When you have independent dummy variables. So I want us to switch to a case where we have a dependent binary variable. In a case where we have a dependent binary variable. So we are looking at the binary dependent variables. And we start by saying that in order to correctly specify specify the binary variable, we define one of the categories. We define one of the categories as what we call the success, as the success outcome, which takes the value 1. The success outcome, which takes the value 1. And the other as, in quotes, the failure outcome, as the failure outcome. Failure outcome, which is equal to, or which takes the value 0. Which takes the value 0. For example, in a bankruptcy study, in a bankruptcy study, you can say bankrupt is equal to 1 for bankrupt firms, and bankrupt is equal to 0 for non-bankrupt firms, for non-bankrupt firms, like that. The same case, in case of gender, you can talk about 1, or maybe, sorry, in the case of, let's say, if you sit for an exam, you can say 1 for passing the exam and 0 for failing the exam, and so on and so forth. Okay. We say that this illustration shows that the term success, we are calling one item here success. This is not a literal meaning of the word success. Okay, it's just a label. So it shows that the term success is just a generic term. Just a generic term referring to the outcome of interest. Okay, because we are calling this as your success outcome when a firm is bankrupt, and bankrupt is equal to 0 when the firm is not bankrupt. Okay, so this is just a label. It doesn't have a literal meaning in this case. Let me say that in the case of binary response, response, or what we call dependent variable, we model the probability of success. So we model the probability of success in this case. And you say that the OLS model is of the form. The OLS model is of the form. So we say that the estimate of Y is equal to estimate of beta naught plus beta 1 estimator x1, the first independent variable, plus all the way to plus beta k estimate xk. Okay, where the estimate of y is the estimated or the predicted probability of success. Is the estimated probability of success. And we can rewrite the above model in the form. We can rewrite the above model in the form. So we can write it like this: the probability that y is equal to 1, given that, given the data. So this is a probability that, this is a probability of success. Remember, y is equal to 1 is the success. Then y is equal to 0 is the failure. So we're talking about the probability. So if I say probability like that, it's the same as probability like that. Probability like that, same as probability like that. Okay. So we're talking about the probability of success if the data is given. See the symbol for conditional probability. So given the data, so this is given by beta naught estimate, plus beta 1 estimate of x1 plus all the way to plus beta k estimate of xk. So the model can be rewritten like that. Then we say that this model is called, so this is called the linear probability model. So this is called the linear probability model, LPM, the linear probability model. Then the interpretation of the regression coefficients here is straightforward. So we can say that the slope coefficients, that is beta 1 all the way to beta k, yeah, indicate the marginal effect. They indicate the marginal effect. That is the effect of the corresponding variable if you hold the other variables constant. So the marginal effect of the corresponding x variable, on the success probability. That is the change in the probability. That is the change in the probability as x changes. So mathematically, you can say this is the same as the change in the probability of success. That is y is equal to 1 given x. This is delta, which means the change in the probability of y is equal to 1. That's the same as probability of success given the data is given by you take beta j, then for change in xi. So as you change the x's, then this coefficient here tells you how much the probability changes. Okay, just like we interpret the usual OLS model or the normal OLS model, the same way. For example, let's say this. We have this illustration: married women participation in labor force. This was in 1975. So let's consider this data of married women participation in labor force, 1975. and we are told to see the OLS estimation of the linear probability model. Okay. Then I want to display that. I want to display this information. So let's consider the data on married women participation in labor force of the year 1975. Then after you fit the model specified up there, you'll have the residual standard error. So you'll have this information here. You'll have the residual standard error, degrees of freedom, multiple R squared, and some other stuff there. Okay. Then the table of regression coefficients and the standard errors is here. So you're given this information there. Okay. So this is what we're given. I want us to consider that example. And I want us to note that all the variables except this last one are significant. As you can see, this is the only variable which is not significant because the p-value is too large. The other variables are significant at the 5% level of significance. Only this variable is not significant. Okay, but there's a problem somewhere, and that's what I want us to illustrate. I want us to write it down. So from the given output, we observe the following. Number one is that all the variables except the last one there, except the variable we are calling kids GE6, except that particular variable are statistically, all the variables are statistically significant with signs as expected. So we have not seen a variable which we expect to have a negative relationship having a positive relationship, and vice versa. So it looks like the model fits well. When you also check the R squared, it's not very bad. It's 26.3, and the p-value is very small. The overall significance of the model is good. The p-value is very, very small. So the overall model is okay. Then we can also note that number two, that the coefficients indicate the marginal effects. They indicate the marginal effects of the variables on the probability of a woman participating in or let's say this of a woman being in of a woman participating in labor force. So that's the variable code there in labor force. A woman in labor force. For a woman who is participating in labor force, then that's what we are predicting, because either a woman is participating or not participating in labor force. Okay, thus we can say, for example, an additional year of education, increases the probability. So let's go back to that illustration. So we are attempting to interpret this coefficient here. So this means that an additional year in education, then the probability of a woman participating in labor force increases by this much. Okay, so that's a very high increase, by the way, if you notice. So that means if education is very high, if the number of years in education is very high, then we have some potential problem. The increase might be more than one, or actually we don't need more than one. We just need around more than 0.4. If the other variables are zero, if everything else is zero, we just need a variable, an increase of around 0.4, which is possible depending on the number of years that you put here. And that means that the probability that we're predicting will be more than one, which does not make sense or which is not allowable. Okay, so that's a potential problem to this model. And that's what I want to mention here. That so thus we're saying that an additional year of education increases the probability by 0.037 when other variables are held constant. So if you hold the other variables constant, that is it. That's a very big increase, huh? And we say that we note that that is a potential problem. That's a potential problem in the estimation of probabilities, huh? Because it is possible for the change to be more than one. So if the cumulative total, if more than one, it means that the probability will be more than one, which might not be making a lot of sense. Okay, so we note that I want us to note the issues associated with this kind of modeling, the linear probability model. What are some of the issues that are associated with this kind of model? Number one is that the dependent left hand side is restricted to the interval 0, 1. So because these are probabilities on the left hand side, while the left hand side is defined within the interval minus infinity to positive infinity. Okay, which may result to probability predictions, less than 0, that is negative values, less than 0 or larger than 1. So that's a potential problem. We may end up predicting values of probability which are more than 1 or less than 0, that is negative values. And we know that probabilities are always numbers between 0 and 1. Okay. All right. Number 2 is the problem of heteroscedasticity. Of the error term or the residual that is U. Since by the by the notation, it violates assumption number 2. It violates assumption number 2 of the classical assumptions of OLS. So assumption number 2 is violated here. Okay. So full stop. Then we can have an illustration of the the marginal effect. So we can have an illustration here. We can have an illustration, a graphical illustration to show the marginal effect of experience and education when the other variables are held constant. And then we'll see how the probability of predicted probabilities might end up being larger than 1. So let's consider the following graphical presentation. So we can consider, let's look at these illustrations. On the left-hand panel, we have the marginal effect of experience on married women in labor force participation. So marginal effect just means that you have held all the other variables constant. So you're only left with, with the experience. So you control all the other variables. And you see that this curve here is quadratic, is quadratic because the curve that was specified up here, we specified a quadratic curve here. So experience is quadratic. As we have experience, then we have experience squared. Is experience squared. So that's why the curve is making a turn. When you look at education, education will give us a straight line because this is just a linear relationship between education and the probability of women participation. So that's why this is a straight line. So what we're saying as potential problems to the linear probability model is that maybe this curve can go down all the way to some negative value here. Maybe you take so many years of experience. Practically, that may not be possible, but theoretically, if you are to predict for a value, let's say 100, maybe the probability curve will be down here, maybe. The same case here, if education maybe was 50, if you are to increase the education level to 50 years, or maybe something like 40, you notice that this curve might be, this is a straight line, so it might be past 1, because we don't expect it to go past here. We don't expect to go past here where we expect 1 to be. So these are potential problems of the linear probability model. Okay, so to solve those kind of limitations, we prefer not to fit these kind of models. So we fit what you call the Logit and the Probit models. And that's what I want us to discuss in our next session. So let's look at Logit and Probit models. And we start by saying that the first of the above problems, that is number one here, can be technically, or can be technically solved, can be technically easily solved by mapping the linear function on the right hand side of the linear probability model. You map it by a nonlinear function to the range 0, 1. So we're saying that instead of allowing the right hand side of the linear probability model to take the range minus infinity to positive infinity, we can transform it using some nonlinear function into this interval, into the interval 0 and 1. Okay, then you say that such a function is called a link function. Such a function is called a link function. It's called a link function. That is instead we write the linear probability model as the linear probability model as something like this. The probability that y is equal to 1 given the data, we write it in this format: G of x, that's a matrix denotation there, G of x transpose of beta. Okay, where G is the link function, that restricts the right hand side to the interval 0, 1. That interval from the entire real line. From the entire real line. So instead of considering minus infinity to positive infinity, we restrict the right hand side to the interval 0, 1. Okay. And we note that although there are many functions, that can do that job, the most commonly used functions are called the most commonly used functions are the so-called Logit and Probit. Logit and Probit. So this type of link functions are the most widely used. Okay, and we say that the former, that is a Logit, is based on logistic distribution. And the latter on the normal distribution. The normal distribution. All of us here are conversant with the normal distribution. Full stop. When we say that economists prefer the Logit, economists prefer the Probit function. So economists prefer the Probit transformation. They prefer the Probit transformation such that G is the distribution function, of the standard normal. Standard normal is what usually not by Z of the standard normal. That is, you have G of Z. You have G of Z. That is, you have G of Z. G of Z is equal to phi of Z, where phi is the symbol that we use for cumulative probabilities. Under the standard normal distribution. So we're talking about something like this. If that's the standard normal distribution, what we are calling phi of Z. If this is Z, then the shaded part is what you're calling phi of Z. So this is Z like that. So it's like the cumulative distribution. So we say that, which results to, so we say that the resulting value are the cumulative, that means cumulative means from minus, this is the standard normal. So this means starting from minus infinity to Z. The cumulative probabilities of success. Let's say of the success outcome for given values of the explanatory variable. Variable or variables. So those are cumulative probabilities, and we are sure that the cumulative probabilities of the standard normal can never go beyond 1. So that's the beauty of this kind of transformation. Okay, then we note that the Logit transformation gives the cumulative probabilities of the success outcome, probabilities of the success outcome for given explanatory variables, variable variables, using the function, so this is a function that you use here. So using the function g of z is equal to e, the exponent of z, divided by 1 plus e of z. How this formula is arrived at is not required for you. So that's the formula that you use to obtain the probability of success of the success outcome for given values of the x variable. So where z, what we are calling z here is this. This is the same. This is the same way of saying. This is the same saying beta 1 x1 plus all the way to plus beta k xk. So that's what we are saying. These are matrix format in a compressed form, but the same as this. So that's what we're saying in the right-hand side of the linear probability model. Let me see if we still have it up there. So the right-hand side of the linear probability model. So this is what we're talking about. Where are those things? Yeah, this is the right-hand side. This is what we are calling in short matrix format. So the same thing. Okay. Then we note that the two transformations, sorry, what did you say? Where z is equal to that. So this is the standard. So this is the standard normal. The standard normal, which usually, or the z score, is the z score, and e is the exponential constant. Is the exponential constant. This is Euler's constant, the number 2.78 something. You always get this value from your calculators. Then we can note that both transformations, that's the Logit and the Probit, both transformations are S-shaped. They are S-shaped. They are S-shaped cumulative distributions. As shown below. I have drawn those things using the computer so I can show you how the distributions look like. You notice that there's no possibility of the probability exceeding 1 or going to the negative. Shown below. So we have these. So on the left-hand side, you have the Probit transformation. And you can see there's some horizontal dotted line up there. And then some horizontal dotted line down here. That is at the point 0, when probability is at the point 0 and at the point 1. And you can see this curve here, this S curve here, can never ever go beyond the point 1. It will always be within 0 and 1. That's the beauty of this kind of transformation. So you have that. So these are cumulative probabilities now. Okay, so start from 0 cumulatively all the way to 1. All the way to 1. The same case with the Logit transformation. As you can see, this is a 0 line down here, the red dots. And then we have the red dots up there showing where 1 is. And clearly this curve can never ever go beyond 1. As you know, this being a standard normal, we know that almost all the distribution is between -3 and +3. If you sketch the standard normal distribution, then you find that the curve is almost at 0 when you are when you go beyond -3 or beyond or above +3. So that's why you can see the curve cannot exceed here. The remaining probability is quite small and can never ever exceed 1. Same case here. This being a standard normal Z, after -3 and above +3, the probability is still within 0 and 1, as you can see here. So there's no way it will ever go above outside the required interval. So this is the beauty of this kind of transformation, and is very much recommended when you are modeling the probability of success, or when you have a binary response variable and your interest is to model the probability of success. So we're saying that we're looking at the interpretation of the regression coefficients for the Probit and Logit models. And we note that the interpretation here is totally different from how we interpreted simple linear or even multiple linear regression, which were fitted using the OLS method. So this is how you interpret. Number one, we can say that holding the other factors constant, holding other factors constant. And we are saying that because this is multiple regression, huh? Because we have more than one independent variable. We say that, sorry about this. Sorry, before we go to the interpretation, I want us to look at something here. So before we go to the interpretation of some regression coefficients, I should say the general interpretation of this kind of curves. So we say that the price, the price we have to pay, that is when you decide to fit this kind of models, then there are some consequences, or maybe some limitations. So the price we have to pay here is the interpretation of the marginal effects. The interpretation of the marginal effects, which is not straightforward. Which is not straightforward. It's not straightforward as in the case of the linear probability model. However, generally speaking, a negative sign on the coefficient, indicates a decreasing effect. Of the probability of observing the success outcome. While a positive sign indicates an increasing effect. So that's a similarity between the interpretation of the linear probability model and the interpretation of the Logit and Probit models. If the coefficient has a negative sign, means that there's a decreasing, there's an inverse relationship, and if it's a positive sign, it means that there's a direct relationship between the predicted value, probability of success, and the independent variable in question. Okay, let me say that in the Logit model, we take exponents. Of the coefficients. And report the resulting values So this statement is very important, and report the resulting values as percentage increase, or decrease, as percentage increase or decrease in something called in the odds of the success outcome. Odds is just the ratio between the probability of success. If you take the probability of success divided by the probability of failure, those are what you're calling the odds of the success outcome. Okay, so so percentage increase or decrease in the odds of the success outcome given the explanatory variables. So if you're given the explanatory variable or variables. So here we report in terms of the percentage change in the odds of success. And odds is just the probability of success divided by probability of failure. Okay, full stop. So this is a very important statement there, because our focus will be in the interpretation of the regression coefficients at this point. Then the Probit regression coefficients. Remember, we said that the Probit assumes some normal probability distribution, so which is a continuous probability distribution. So the interpretation is quite different from the one of the Logit. So we say that the Probit regression coefficients give the change in the z-score. They give the change in the z-score. They give the change in the z-score, or what we call the Probit index. The Probit index for 1 unit change in this case we assume in the change of a continuous predictor. So if your predictor is continuous, that's how you interpret the coefficient. The change in the z-score or the Probit index for 1 unit change in the predictor, and the predictor here must be continuous. Okay. Then we say that dummy variables have a slightly different interpretation. So we say that dummy variables have a slightly different interpretation. So it's good for you to note that. Because now when you're talking about, if you're predicting the probability of success using a dummy variable, then you must be mentioning the probabilities, the change in the probabilities of the dummy variable in reference or in comparison to the reference category of the dummy variable in question. So for instance, you'll be talking about the probability of success for the females compared to the males if gender was one of your explanatory variables. So the interpretation there is slightly different. Now let's have an example to show how we can interpret regression coefficients. So example, I'm going to display some given output. Then our focus will just be to interpret the coefficients. So this is the output that we used to draw the diagrams that I've shown you up there. So let's consider this example, which shows the Probit and Logit estimation of married women participation in labor force. The probability of married women labor force participation. So this is the Logit model. We have the intercept, the husband wage, education level, experience squared. So experience is quadratic, age. Then we have this variable kids kids LT6, kids GE6. Okay, so the description of the variables is given somewhere, but for now our focus is the interpretation of these coefficients. So I've given the interpretation here. So how do we interpret the regression coefficients? So we say that holding the other factors constant for every, this is for every unit increase, that is for every additional dollar in the husband wage, the odds of women participation in labor force decreases by, so we're interpreting the coefficient for husband wage, this one, which has a negative sign. That means that as you increase the husband wage, then the probability of women participation in labor force goes down. And we say that you take exponents. You take exponent of that value. When you take the exponent here, you'll get, if you take the exponent of 0.04, I mean minus exponent of minus 0.043802. If you take the exponent there, you'll get 0.9571. So that tells you that the decrease, the amount of decrease is 1 minus that value. So 1 minus 0.9571, which is 0.04281. And then you convert this into percentage, which gives you 4.29%. Okay, so holding the other factors constant, for every unit increase, that is for every additional dollar that is earned by the husband, this should be husband wage, the odds of women participation in labor force decreases by 4.29%. That means that for women whose husbands are earning higher, then those women are less likely to participate in labor force. Okay, so that might make sense. If you consider situations or societies which are male chauvinistic, which is not a good thing anyway. Then Roman 2, we can say that holding the other factors constant for every additional year of education level, so interpreting the education level of the women, the odds of women participation in labor force increases. So if you look at here, the coefficient is positive. That means there's a positive relationship between education level and the participation of women in labor force issues. So we say that holding the other factors constant for every additional year of education, the odds of women participation in labor force increases by, you take the exponent of the coefficient. Then you minus 1 so that you can know the percentage increase. You minus 1 so that you can get the percentage increase, which is 0.23, which is the same as 23.28% increase. Okay, then I've asked you to interpret the other coefficients. Then using the Probit model, if you fit this, if you fit that data using the Probit model, the coefficients will be different, as you can see here, because the transformation is different. So we have these values there. Then we say the interpretation of the coefficient, we say that for 1 unit increase in the husband wage, the Z score. So in the case of Logit, we were talking about the odds, but here we're talking about the Z score of women participation in labor force decreases by this value here, where this value here is the coefficient we have here. So the negative here tells you it is a decrease, but decreases by how much? 0.0255 etc. Okay, and so on and so forth. The number 2, we have for every additional year in education, the Z score of women participation in labor force increases by 0.1248347. I think the actual interpretation of what the Z score here could mean might not be straightforward. But from what we discussed in business statistics 2 is that the Z score is just the number of standard deviations above or below the mean, basically that. So it's just the amount of the standard deviation of, the number of standard deviations above or below the mean, and so on and so forth. Then I've asked you to try and interpret the other variables. So guys, that marks the end of today's class. I don't know whether we have any questions. If we do not have any questions, we'll be meeting next week for our next class.